Okay, so number 29 asks you to find which of the following statements about the electric field is true at these 2 points. And because this is a hollow metal sphere, the answer is A, and it's 0 at both points because wherever you are in a hollow metal sphere, the electric field is 0.
Alright, for number 30, it asks to find the direction of the electric field at the origin, and assuming that it is a positive charge, it'll be going away in the it'll be going down in the y direction because of the positive q charge, and towards the positive x direction because of the negative q charge. Therefore, its net direction will be D.
Okay, so if you're trying to find the magnitude of the electric field at the origin, well, you know that the direction is pointing down to the right, so you can just use it as a hypotenuse, and the two legs will be the 2 points, the 2 lines that you have right now, and each line will be kq over r squared, and if you square those, add it together and square root it, you get root 2 kq over d squared.
Okay, for 32, it asks what will the electron and the proton have the same in the electric field, and because the electric field is constant, the magnitude of the force acting on them will be the same, and nothing else will be the same because an electron and proton have different charges.
Okay, so to solve number 33, you can use the equation E equals V over D, and what you do is, so your V, the difference in V would be 10 minus 2, and D would be 0.04, so you get E equals 200, and you do 200 times 0.01, which is the distance, equals 2, and then you also have to add 2, because the bottom plate is 2, so the answer is 4. And then for 34, the magnitude of the electric field at point P, that's just E that we solved, which is 200.
So for 35, a particle of charge Q and that goes through is accelerated from rest to a potential difference V. If the charge is doubled and the mass is halved, the potential difference will be d2k because the mass does not affect the potential difference.
Okay, so you have electric field lines, and they're asking you to find which one is true. And the first thing you would do is you find out which one's positive, which one's negative, and you know one's positive, one's negative because they run into each other. And you can see for the Z one that the arrow is actually pointing towards Z, so you know that one's negative, and the Y one, the arrows are pointing away, so that's positive. And the only answer choice that makes sense here would be D. A small negative charged object placed at X would tend to move to the right, and it would move to the right because Z is negative and X is negative, so they would push it away from each other. Wait. Okay, so a hollow metal sphere, 1 meter in diameter, carries a charge of 4. The electric field at a distance of 2 meters. Well, you can just use kq over r squared. So your k is 4, your k is 9 times 10 to the 9, q is 4 times 10 to the negative 6, and then your r is just 2 squared, and you end up with the answer A.
And then 38 we didn't learn, but 39, the electric field E just outside the surface of a charged conductor is... Oh wait, that one's conductor. Alright, so we're given the two charges Q1 and Q2 on the x-axis at 0.2. Q1 has a charge of 8 microcoulombs, and then we're told the net electric field is 0 at point P. So the first question is to determine the magnitude of the sign of charge Q.
Okay, so because we know that the net electric field at point P is 0, if we can use the equation kq over r squared for both of them, and if we set them equal, if we add them together, we can get 0. And once you simplify out this equation, you get q2 is equal to negative 2 times 10 to the negative 6, which is 2 microcoulombs, which is your answer.
For part B, determine the magnitude and direction of the net force on charge Q.
Okay, so the formula for net force is KQQ over R squared, and you just plug in the numbers, including the one that we just got, the last question, and then you just end up with 3.6 newtons, and you have to specify it's to the right because you know that the force will go from positive to negative.
Part C, calculate the electrostatic potential energy of the system.
Okay, so we only have two charges, so we only need to do it once, and the formula is V equals KQQ over R, and if you just plug it all in, you get negative 0.72 joules, and you have to make sure that you actually use the negative from the charge, because here it actually matters.
Part D, determine the coordinate of the point R on the x-axis between the two charges at which the electric potential is 0.
Okay, so the formula for electric potential is KQ over R, and if we're trying to find the coordinate of point R, you can just set one of the distances to R and the other one to 0.2 minus R, because when you add them together you get 0.2, and then when you plug in everything and you simplify out, you get 10R equals 1.6, so R is 0.16 meters from the left.
And then the last question, how much work is needed to bring an electron from an infinity point to R, which was the R point that was determined in the previous question.
Okay, so work is Q times delta V, and at infinity, your V is 0 because your R will be infinity, and if you're at R, we already know that the potential is 0, so work times Q times 0 minus 0 will be 0. Yeah.